Hello, I'm back with a few more thermodynamics questions. It looks as though this first one's going to be all calculations, so that should be pretty straightforward. Normally the calculations are the easy bit. So for part A, they've given us the molar mass of hydrogen gas. We need to calculate the mass of a hydrogen molecule. Right, so the molar mass is the mass for Avogadro's constant number of molecules. So if we divide this mass, this 2.02, times 10 to the minus 3 kilograms per mole. So now we need to divide by the number of molecules in a mole, and then we're going to get our mass per molecule. So what is that coming out at? So 3.35548, so 3.4 times 10 to the minus 27 kilograms. And then it's one of those ones where you think about the units. We've been given kilograms per mole. So if we then divide by molecules per mole, so divide by molecules per mole is the same as multiplying by mole over molecules, in which case we're then getting kilograms per molecule. So it's the same old thing of checking your units if you don't know which way up to put everything. Right, part B, the temperature of the Earth's upper atmosphere is about 1100 Kelvin. Show that at this temperature, the mean kinetic energy of an air molecule is about 2 times 10 to the minus 20 joules. Right, well, this we can use our 3 over 2 kT. So our average energy is 3 over 2 kT. So that's 3 over 2 multiplied by Boltzmann constant, so 1.38 times 10 to the minus 23, and then multiply out by our 1100 for the temperature, which gives us 2.277 times 10 to the minus 20, so 2.3 times 10 to the minus 20 joules. Two significant figures again as we add up here. Right, show that the speed of a helium atom of that mass at that temperature is about 2.5 kilometers per second. Right, so now we're just stepping this up to say, well, this, what we've just worked out here, this is the energy, the average energy of some of a particle at that temperature. So if we've now got a helium atom, the kinetic energy, half mv squared, is going to be equal to that 2.277 times 10 to the minus 20. So we got half of the mass, which is 3.3 times 10 to the minus 27, times v squared is 2.277 times 10 to the minus 20. So we just need to divide through by the 3.3 times 10 to the minus 27 and then square root, which is going to give us that v is 2.6 times 10 to the 3 meters per second, which is roughly equal to 2.5 kilometers per second, which is what we had to show. Right, the last calculation then, so this isn't a calculation actually, we've got to explain in it. So the escape velocity from Earth is 11 kilometers per second. The escape velocity is the minimum vertical velocity a particle must have in order to escape from the Earth's gravitational field. Explain why helium atoms still escape from the Earth's atmosphere. Right, so we've said here that this is average energy. So you want to say, yeah, this is average energy. So we do, therefore, some helium atoms will have energy greater than this, or even much greater than this, and therefore will have velocity much greater than 2.5 kilometers per second. So that's the thing, it's all because it's average energy. So that's the key point that you want to put in, and then following that chain through, saying therefore some of them have got more energy, so some of them have got a lot more velocity. There we go. So just some calculations to warm us up. So what have we got up next? Next, we have to define the kilowatt hour. Right, there's two ways you can go about this. I don't like just saying, oh yeah, 60 times 60 times 1,000 joules. That seems kind of lame. It's not really giving any insight in it. So let's say that it is the energy supplied by a 1 kilowatt device or supply in 1 hour. So, and then you could say, I suppose, i.e. 60 times 60 times 1,000 joules. All right, domestic refrigerator works at a mean power of 70 watts. Calculate the cost of running this refrigerator for 1 week at a cost of 12p per kilowatt hour. So we need to work out, well, how many kilowatt hours we've got. So that means we're going to have 70 times 7 times, what have we got? Yeah, 70 times 7. So that's the power time, that's days in the week. Then we got to do hours in the day, minutes in the hour, seconds in a minute. So that is the energy that we've got. That's our total energy. If we then divide that by our energy in a kilowatt hour, as in our 60 by 60 by 1,000, that is going to give us our kilowatt hours. So we've got a lot of things that have cancelled here. Boom, 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 boom. So that's quite good. We can get rid of that and that. So we've got 49 times 24 over 100 kilowatt hours, whatever that ends up working out to be. And then we've got 12p kilowatt per kilowatt hour. So if we multiply by 0.12, that's then going to give us our total amount of money, which is coming out at £1.41. So not very much, which is what you'd hope if you're running a fridge. You don't want fridges to be particularly expensive, since we've got them turned on all the time. Part B, a large jug containing 2 kilograms of milk is placed in a refrigerator. The milk cools from 18 degrees C to 3 degrees C over a time period of 100 minutes. There's the specific heat capacity. Calculate the thermal energy removed from the milk as it cools. Right, so that is going to be MC delta T. So that is 2 multiplied by 3800 multiplied by the change in temperature is 15 degrees. So that comes out at, we got 114,000. So 114 kilojoules, whatever how you want to put it, doesn't really matter. The rate at which this thermal energy is removed from the milk. So how long was this for? This is over 100 minutes. So we need to divide that by 100 times 60 to get it into watts, because that's our joules per second. So that is going to leave us with 19 watts. So some fairly basic calculations. Part C, another container full of milk is placed in a freezer, cooled from 18 degrees to minus 18 degrees. Assume that the thermal energy is removed at a constant rate and that the freezing point of milk is 0 degrees C. The specific heat capacity of milk below 0 is significantly less than its value above 0. On figure 3.1, sketch a graph to show the variation with time at a temperature of the milk over that range. We don't need numbers, right? So the key thing is, how steep are we going to make the gradients? They've told us that we have got a significantly lower specific heat capacity once it's frozen. So if the specific heat capacity is lower, that means the temperature is going to change quicker, because there's a smaller energy difference for each step in temperature. So that's what we're going to see. So if we've got, let's just draw in our first line where they don't care, we're starting at 18, we can put in, that's going to be a straight line. So we've got this constant cooling rate, this constant gradient coming down here. Then it freezes. That's when we get the flat bit while we're going through our latent heat. The issue then is the state of the gradient. Is it going to be steeper or shallower once we're below 0? So we're going to get a quicker temperature change with time because the specific heat capacity is lower. So we need a steeper gradient. Okay, maybe not that steep. Again, I'm having trouble drawing these straight lines on here. So let's go for something like that. So that has to be a steeper gradient than the one that we've got when it is still in liquid phase. So yeah, we want a graph shallowish, flat, steep. That's what we're looking for. Cool. So that's the second one done. Let's just keep pushing on. We've now got a student investigating Brownian motion by observing through a microscope smoke particles suspended in air. Describe the behavior of the smoke particles as observed by the student. Right. So we need, well, they jiggle around. They move in a random. So you want to put random. Certainly want to include that. Jiggling is a word that I know they like on the mark schemes, a random jiggling manner. So you don't need a lot for that. They're only asking for 1 mark's worth of answer. State how the observations lead to conclusions about the nature and properties of the molecules of a gas. Right, so the random motion, we can pick out various bits, you see. So you can have the random motion. That implies that we've got hit by random, yeah, let's go hit by randomly moving air molecules. Randomly moving air molecules. So we can link those bits together. We've got that the jiggling, so that's the other thing that we've mentioned, / small movements. That's suggesting that it's getting hit from all sides. So hit from all sides with sort of random variations. Random variations. And the other thing that we can say is that, well, we can see the what were they saying? Smoke particles in this one, isn't it? We can see the smoke particles, but not the air molecules. But not air molecules. So we can say, well, they're really small. We can't see them. They've got to be pretty. That implies that the air molecules are very small. So that should cover all bases there. Right. Part B. The molar masses of hydrogen and oxygen are those, respectively. The mean speed of hydrogen molecules at room temperature is 1800 meters per second. What's the mean speed of oxygen molecules at the same temperature? Right. So if you've got if they're at the same temperature, so we've got E is proportional to T. Therefore, they've got the same energy. So we've got oxygen that's going to be 16 times heavier than hydrogen. Therefore, it's got to be 4 times slower because the mv squareds have got to be equal to each other. Half mv squared equals half mv squared. So those things have got to be equal. So for the oxygen and for the hydrogen. So therefore, we've got a quarter of 1800. 1800 divided by 4, which is going to be 450 meters per second. So another fairly simple calculation. I think I actually leave that there with 3 because I see I've got 2 more on this set of slides. So I'll come back and do those 2 in the next video. But yeah, these thermodynamics questions are pretty straightforward. They go through the same things over and over again. They don't really get into the nitty-gritty of the real details of understanding thermodynamics in these exam questions. So yeah, they're usually pretty easy.